Welcome to this explainer. I am so thrilled you're tuning in today. We're going to embark on this incredible, kind of hidden industrial journey that sits right behind literally every single clear, sparkling glass of wine you've ever enjoyed. For most of us, we just pop a cork, pour a glass, and marvel at how pristine the liquid looks, right? But getting to that point of absolute clarity, wow, it is a relentless, microscopic battle. So let's just dive right into it. Actually, let's be real for a second. Have you ever wondered why your wine isn't just a cloudy, chunky soup? Because honestly, directly after fermentation, that is exactly what it is. It's this unappetizing, hazy swamp just filled with floating yeast corpses, lingering bacteria, and organic debris. I mean, if a winemaker just bottled it straight out of the vat, you'd literally be chewing your Cabernet instead of sipping it. But instead, we get this. Our ultimate goal is physical perfection, a pristine, perfectly stable glass of wine that catches the light, looks appetizing, and is structurally sound. Contrasting that cloudy fermentation soup with this pristine finish line really sets up the epic quest for clarity we're going to explore today. It's all about that transition from biological chaos to absolute aesthetic and physical perfection. Okay, so here is our mechanical roadmap for the explainer today. 1. The quest for clear wine. 2. Depth and absorption filtration. 3. The tangential filtration revolution. 4. Absolute membrane microfiltration. And 5. Flotation and centrifuge alternatives. Starting off with Section 1, the quest for clear wine. All right, before we even look at the filters, we got to define the enemy here. We need to know what exactly is ruining the wine's shelf life and clouding up its aesthetics. And the technical term for this enemy? It's turbidity. Turbidity is basically just the degree of clarity a liquid loses because of all those suspended particles floating around in it. And in the winemaking world, we don't just guess how cloudy a wine is by eyeballing it. No way. We measure it using NTUs, which stands for nephelometric turbidity units. So the absolute crucial takeaway here is that NTUs are the primary metric we're fighting against. We have to drive that number down if we want to achieve true physical, chemical, and microbial stability. So what's actually floating around in there driving those NTUs up? Well, meet the usual suspects. First up, we've got lees, which is honestly just the polite winemaking term for dead yeast that clumps together after alcohol fermentation. Then we have lactic acid bacteria, various floating proteins, pectins, glucans, and even mucilages and gums. If left unchecked, these suspects will inevitably cause physical precipitation in the bottle. Or worse, they trigger unwanted microbial reactions that just completely ruin a wine's smell, taste, and appearance over its shelf life. And all of this builds toward a super important number in winemaking, 10 NTUs. See, before a wine can undergo cold stabilization, which is this process where the winemaker drops the temperature down to -4 degrees Celsius to safely crystallize out potassium bitartrate salts, the wine must be brought down to an NTU of 10 or less. Because if the wine is too cloudy, the cold stabilization just won't work effectively. Basically, you got to clean the house before you freeze it. Moving right along to Section 2, depth and adsorption filtration. This right here is our very first line of defense. We're talking about the older, heavy-duty roughing methods to take out the biggest chunks of debris. Imagine a really thick, porous sponge. Instead of just catching things on the surface, depth filtration uses the entire thickness of the filter bed. Think of it kind of like a club bouncer at the front door, but with a super long, winding hallway behind him. As the wine travels through these totally tortuous paths, the filter physically blocks and chemically absorbs those large, unruly particles. Now, a super popular method for this is using diatomaceous earth, which, crazy enough, is actually the fossilized remains of microscopic algae called diatoms. To catch those obvious crowds of sediment, this process requires 2 stages. First, you have the pre-coat, which establishes the initial filter bed using about 0.7 to 1 kilogram per square meter. But here's the thing. As the wine filters, that bed gets clogged up fast. So winemakers continuously add a body feed of 0.4 to 1 gram per liter as the wine flows. It's constantly building this fresh labyrinth of earth to trap the debris. Pretty clever, right? Besides that fossilized earth, winemakers also use other adsorbent materials. We're talking thick cellulose pads, fiberglass, or sometimes activated carbon. Though, honestly, carbon is pretty rare in high-quality wines because it can accidentally strip out way too much character. Now, while these materials are incredibly effective at grabbing electrically charged molecules, there is a catch. This is considered an open filtration method. Because it often involves open equipment, it carries a slight risk of wine oxidation. And oxygen, that is the slow killer of a fresh wine. So winemakers have to be incredibly careful here. All right, let's jump into section 3, the tangential filtration revolution. So because earth filters can be really messy and carry that risk of oxidation, the industry has seen a massive shift toward this, a highly efficient, modern hero of the winery. You see, if you try to ram a dirty, particle-filled liquid directly perpendicular into a filter, it's going to clog almost instantly. But the absolute brilliance of tangential filtration is in the geometry. Instead of ramming the wine into the filter, the liquid is cleverly recirculated parallel to the filtration membrane. It's a total game changer. Let's break down this 3-step semi-automatic loop real quick. Step 1, the turbid liquid feeds continuously parallel or tangential to the membrane, rushing right past it like a river. Step 2, only the perfectly clean wine, which we call the permeate, manages to slip perpendicularly through the microscopic pores. And step 3, the dirty leftover liquid, the concentrate, doesn't clog the pore. It just gets swept away by the current and goes right back to the source tank to be cycled again. This constant, rushing, sweeping motion prevents the filter from clogging up quickly. And the results? I mean, they're absolutely staggering. Look at this metric, 0 to 1 NTU. Tangential filtration can literally take a highly turbid, muddy wine of over 200 NTUs and bring it straight down to our pristine finish line of less than 1 NTU in a single pass. It is a technological marvel. It saves time, reduces oxidation, and practically eliminates the need to buy and dispose of tons and tons of fossilized earth. Next up, section 4, absolute membrane microfiltration. Okay, so the wine looks clear, but is it actually microbially safe? We have finally reached the climax of our journey, the final boss battle against microscopic infiltrators. Think of an intricately folded microfiltration cartridge as the ultimate high-tech ID scanner at the final door before the wine goes into the bottle. Here, the flow actually goes back to a direct perpendicular push. The wine is forced through microscopic pores made of materials like polyether sulfone. And because it's so tightly pleated and folded, it has a massive surface area to catch absolutely specific, tiny biological threats. And when I say specific, I mean we're dealing with exact micrometer sizing here. To guarantee total elimination of specific yeast and bacteria populations, these membranes have to be extraordinarily tight. Let's say a winemaker wants to eliminate Oenochus oeni bacteria. They'll use a 0.45 micron cartridge. To catch Saccharomyces cerevisiae yeast, a 0.65 micron pore works perfectly. For Brettanomyces, which is that yeast that can give wine a funky barnyard smell, a 1 micron cartridge is absolute. If a microbe is even a fraction bigger than that specific pore, it absolutely cannot pass. No way. But how do we know it's actually working? Well, we use a metric called the logarithmic reduction value, or LRV. This measures a filter's success rate. Think about it. If you push a wine containing 100,000 microbes into the cartridge, so that's 10 to the 5th power, and only 10 microbes manage to come out the other side, you've reduced the population by 4 powers of 10. So your LRV is 4. This proves mathematically just how many thousands of microbes get trapped right there in the cartridge folds. Now, before a wine is ever allowed to touch that expensive absolute membrane, it has to pass a strict final exam called the fouling index, or FI. And hey, don't let the math formula scare you. It's basically just a test to see how quickly the wine slows down when pushed through a tiny test filter. You just measure the time it takes for 200 milliliters to pass, and then 400 milliliters, and plug it right into the equation. And here is the golden rule. That fouling index has to be less than 20. If the FI is higher than 20, the wine fails the test. Why? Because those absolute microfiltration cartridges are incredibly expensive. If the FI is too high, it means there are still too many hidden colloids or tiny particles floating around in there, and that pricey cartridge is going to clog almost immediately. If a wine fails, the winemaker literally has to send it back through a pre-filtration skid to clean it up further before trying again. It's a tough test. Finally, let's hit section 5, flotation and centrifuge alternatives. So while filtration really is the star of the show, there are a couple of other heavy industrial methods used to clean musts and wines that rely on gravity and gas rather than physical barriers. Decanters and centrifuges spin the wine at incredibly high speeds, using centrifugal force and density differences to separate out the solids. The downside, though, spinning it violently often introduces oxygen, which carries a pretty high oxidation risk. Alternatively, there is this brilliant method called flotation. Instead of spinning, winemakers inject tiny bubbles of nitrogen gas into the bottom of the tank. These gas bubbles act like little microscopic life preservers. They grab onto the solid particles and float them straight to the top of the tank. allowing the clean liquid to just be easily pumped out from the bottom. So, what's the big takeaway from all this? Basically, winemaking isn't just about romantic vineyards and looking at wooden barrels. It's a rigorous, high-tech science. Next time you sit down and enjoy a perfectly stable, crystal clear glass of wine, take a moment to hold it up to the light. Ask yourself, how many microscopic labyrinths, tangential rivers, and absolute cellular barriers did this wine have to conquer just to get to you? It really makes that sip taste a whole lot more victorious, doesn't it? Thanks so much for exploring this with me today, and keep your curiosity as clear as your wine.